Building a complex software system is an exercise in managing chaos. Projects routinely run over budget, miss deadlines, or collapse under their own weight. Welcome to our deep dive into software costing. Our goal today is to replace intuition-based guesswork with objective, mathematical science. To do that, we examine the constructive cost model, universally known as COCOMO II. COCOMO II is an empirical, algorithmic cost estimation model. It was derived by analyzing vast datasets of real-world software projects to find the mathematical formulas that best fit actual incurred costs. When managing millions of lines of code, human intuition breaks down. We require objective mathematical models to predict costs accurately and prevent massive financial loss. COCOMO II is structured as a dynamic suite of 4 distinct submodels. At the start of a project, engineers often lack a defined architecture or explicit requirements. As development progresses, the fidelity of the available data improves. Vagueness resolves into explicit system components. Different levels of data fidelity require entirely different mathematical approaches at each stage of the lifecycle. Estimation accuracy mathematically scales and tightens in direct correlation with the progression of time and data fidelity. We can visualize this chronological progression across 4 models: application composition, early design, reuse, and post-architecture. The first stage is the application composition model. Engineers use this during early prototyping or when building systems by composing existing scripts and database programs. Because there is no source code to count yet, the core unit of measurement here is the application point, referring to high-level elements like user screens or generated reports. To calculate the base effort, we divide the total number of application points by a standard developer productivity rate. We then adjust that initial calculation downward based on the estimated percentage of code that the team expects to reuse, rather than write from scratch. This model relies on broad-stroke functionality metrics because the underlying system architecture does not yet exist to be measured. Once the core requirements are agreed upon, but the detailed architecture is still forming, we move to the early design model. Here, the measurement unit shifts to function points. The model applies a formula to mathematically convert these functions into an estimated number of lines of source code. Because the project is still in its infancy, the early design model uses a simplified set of just 7 multipliers to generate a rough cost estimate. Running parallel to this is the reuse model. Modern software is rarely written entirely from scratch. This model calculates the specific effort required to integrate existing code into the new project. Black box code drops in as is, requiring 0 effort. White box code requires active effort to modify and integrate. The output metric here is ESLOC, the equivalent number of lines of new source code, representing reuse effort as if writing new code. Both the early design and reuse models act as a bridge, translating functional requirements into quantifiable code generation metrics. Finally, once the system architecture is firmly locked, we arrive at the most detailed phase, the post-architecture model. The master mathematical formula for this phase states that effort equals A times size to the power of B times M. The exponent B represents the nonlinear complexity of scaling up large software projects. Costs do not scale linearly with project size. The value of B is determined by 5 scale factors: precedentedness, development flexibility, architecture and risk resolution, team cohesion, and process maturity. Consider a textbook scenario, a new team with undefined processes and little risk analysis. Scoring these factors yields 16. The formula translates that score. 16 divided by 100 plus the base of 1.01 results in a final B exponent of 1.17. Highly qualitative factors like team cohesion and process maturity mathematically compound to alter the raw time required to write code. The final variable in the equation is M, the multiplier. M is calculated from 17 specific product, process, and organizational attributes known as cost drivers. This table shows cost drivers on a baseline of 128,000 lines of code, initially estimating 730 person-months. High reliability and complexity push the adjusted estimate to 2,306 person-months. Conversely, low complexity and high tool use shrink the requirement to only 295 person-months. Producing the exact same volume of code can result in a 780% difference in cost, dictated by environmental context and tooling multipliers. Estimating effort in person months is only half the process. The COCOMO schedule formula links those person months to actual calendar delivery months. This brings us to a common management error, the assumption that if 4 people take 13 months to finish a project, adding a 5th person will proportionally speed it up. Brooks's law states that adding personnel to a late software project makes it later. New staff yield diminishing returns. There is a mathematical cost to human labor. Every new team member causes exponential increases in communication overhead and creates new, complex interfaces between team members. The COCOMO mathematics confirm this reality. Doubling the size of your staff will never halve your development time. Human labor in software engineering is not perfectly divisible. Communication complexity acts as a mathematical limit on how far a schedule can be compressed. Beyond the algorithmic cost models, we must look at the business strategies that often supersede them. One strategy is pricing to win. A company bids on a contract based on what the client expects to pay, then reverse engineers the system's functionality so that the development costs fit that fixed price. Estimation also depends on project structure. Traditional plan-driven development requires rigid schedules, while agile planning adapts to changing requirements. A mathematically perfect COCOMO estimate is useless if the chosen development methodology or the business contract misaligns with the project's reality. These variables form the cone of uncertainty. Early in a project's timeline, cost estimate variance is wide, but narrows precisely as architecture locks. The 4 COCOMO submodels map onto this timeline, bringing wild early estimates into strict mathematical focus. When assessing a project, remember the core mathematical drivers: exponent b, accounting for exponential complexity, and the 17 cost drivers that make up the multiplier m. And always remember the human element, dictated by the staffing paradox. Pouring raw labor into a project cannot defeat the mathematical reality of communication overhead. Software engineering is the rigorous, objective management of economic variables and human limitations.